In this video, we're going to prove the theorem entitled the Gram-Schmidt Process. Since it's a process, that means what we're going to prove is called the type of proof is called a constructive proof. Now basically, we have that W, the non-zero subspace of Rn, with our basis. And the basis is S. Once you have that basis S, then there exists an orthonormal basis T for W. And we're going to show how to develop this basis T. So let's write this down. This is a constructive proof. That is, we will develop the set T. Okay. Now, it's ridiculous to find an orthonormal basis first, because finding an orthogonal basis is easier, and then once we have the orthogonal basis, we can normalize every vector in this orthogonal basis, and then we'll have an orthonormal basis. So let's write this down. First, we will develop an orthogonal basis, let's call it T star, that equals to, say, V1, V2, up to V sub n. We're going to construct this. Okay, so let's go and construct it. The first thing we're going to do is we're going to let V1 equal, say, U1, the first vector in the basis S, equal U1. Okay. And there's no problem there because U1 doesn't have to be orthogonal to anything yet. Anything else we add will make sure that it's orthogonal. Okay. Now, so we have V1. So let's work on V2. Let V2 be in the span of the set that contains U1, V1, V1, and the next U vector, U2. So there exists C1 and C2 in the rails such that V sub 2 is equal to C1 V1 plus C2 U2. Okay, now we want V1 and V2 to be orthogonal. We want 0 to equal to V2 dot V1, which, by the way, is the same as V1 dot V2. Now, V sub 2 is this. Okay, it's C1 V1 plus C2 U2 dotted with V sub 1. So we have this dotted with that. That's going to be C1 V1 dotted with V1 plus this dotted with V1, which will be C2 U2 dot V1. Now, V1 is equal to U1, and U1 is in the basis S. Okay, U1, U sub 1 is in our basis S for W. That tells us that this doesn't want to move. Okay. That tells us that U sub 1 can't be 0. The 0 vector cannot be in the span, cannot be our basis element, because that would make the set not linearly independent. It would make the set dependent. So we know that U1 is not 0, so V1 is not 0. And we know that so V1 is not 0. And the only way you dot a vector with itself and get 0 is if and only if the vector is 0. That tells me that the whole dot product is not 0. So I can solve this equation. Remember, it equals 0. I can solve this equation for C sub 1. C sub 1 is, bring this to the other side, is negative C2 U2 dot V1 over V1 dot V1. Okay? That implies that V sub 2, how about we let C2 equal 1? That implies that C1 is negative. If this is 1, it goes bye-bye. The property of multiplying by 1. So C1 equals this. But that implies that we have V2 nicely now. That implies that V sub 2 is equal to C1 times V1. So it's negative U2 dot V1 all over V1 dot V1. That's the scalar times the vector V1 plus, now where are we? We said that C2 is 1. So right here, I have 1 times U2, which is just U2. Okay, so that's V sub 2. Now, let's see if this is actually working. You don't have to check this, but let's check this. Let's see if V2 dot V1 is really 0. Maybe we messed up. U2 dot V1 over V1 dot V1 times V1. I'm just recopying this, plus U2. Well, I dot this with V1. And what I get is this dotted with V1. So I get the scalar, which happens to be its own dot product, times V1 dotted with V1. V1 dotted with V1 plus U2 dotted with V1. U2 dot with V1. Well, turns out that cancels, and you're only left with the numerator for the first term plus the second term is U2 dot V1. Yeah, that's 0. That really is 0. So you don't have to have this. Okay. So now we have V1 and V2 orthogonal. This is great. So V1, V2, and let's throw on U3. We want V3 in the span of that set. That implies, now I have a habit of always using the same coefficients, the same scalars. And maybe I won't do it this time. V3 is a linear combination of those vectors. It's D1 V1 plus D2 V sub 2 plus D3 U3. That's V3. Okay, now we want two things to be true. We want V3 v3 dot v1 to be 0, and we want v3 dot v2 to be 0. We want that. It has to. Otherwise, v3 can't go into this set. It won't be an orthogonal set. Okay. So what do we do? Okay, let us compute v3 dot v1, and we'll make it equal to 0. d3 is this. Okay, d1 v1 plus d2 v sub 2 plus d3 u sub 3. I dot this with v1. So I get this dotted with that. That's d1 v1 dot v1. Then I dot this with this. But v2 dotted with v1, we already know that those are orthogonal. But let's write it down. d2 times v2 v1. That's 0. Plus d3 u3 dotted with v1. And if this is 0, the scalar times the 0 vector is the 0 vector. And we want this to equal 0. So let's call this equation 1. We get d1 v1 dotted with v1 plus d3 u3 dotted with v1. This is equal to 0. Okay, wonderful. So that came from v3 dot v1. Now let's consider v3 dot v2. We would just love for that to be 0 as well. Okay. So v sub 3 dot v sub 2. V sub 3 from right over here is d1 v1 plus d2 v2 plus d3 u3, that's v3, dotted with v2. Well, this is going to be this dotted with v2, d1 v1 dotted with v2, plus this dotted with v2, d2 v2 dot v2, plus d3 u3 dotted with u3, d3 u sub 3 dotted with u2. Okay, v2. Okay. As I said, this dot product is 0. d1 times the 0 vector is 0. And we want this to equal to 0. So we have this equation. We have, let's call it equation 2. We have d2 v2 dot v2 plus d3 times u3 dot v2. This is equal to 0. So we have these two equations. I want to point out why, before I go further, why v2 is not the 0 vector. Let us look at this, equation for v2 right here. Now, v1 is u1, and u2, well, that's u2. And those two vectors are in or basis. v2 is a linear combination of those vectors. Now, you may say, oh, you need all the vectors. Fine. Plus 0u3 plus 0u4 all the way down to 0u sub m. So now I have a linear combination using all the vectors in S. The only way this can be 0 is if all the coefficients are 0. Okay? That's 0. All of these are 0, that one 0, that one 0. This one may be 0. This one here may be 0. But you know what? That's 1. That's 1. So V2 being a linear combination of all the vectors in set S, if it equals 0, well, that can't be. This can't be. It would require all the coefficients to be 0. That coefficient of U2 is not 0. So V2 is not 0. Okay, and it says it. V2 equals this mess, which is not equal to 0. So V sub 2 is not 0. That means V2 dot V2 is not 0. The only way you can dot product vector with itself and get 0 is if and only if that vector is 0. Okay. So I know from equation 2 that V2 dot V2 is not 0. And I also know that V1 dot V1 is not 0 because V1 is really U1. And if you dot U1 with itself, you won't get 0 because the only way you get 0 is if U1 is 0 and U1 isn't a basis for W, hence U1 cannot be 0. Okay, which means V1 is not 0. Okay, so from equation 1, we'll solve for D1. D1 is equal to, bring this to the other side, negative D3 U3 dot V1 all over V1 dot V1. And let D sub 3 equal 1. So we get that D1 is equal to negative U3 dot V1 all over V1 dot V1. So we have D1. And from equation number 2, since that's not 0, we can solve for D sub 2. It is equal to, when we bring this to the other side, it is negative D3 U3 dot V2 all over V2 dot V2. But if we let D3 equal 1, then D2 is negative U3 dot V2 over V2 dot V1. Think about the fact that equation 1 up here equals 0. We can say, for example, that D3 is 1. We can say that's 1. Think why that's true. It's not that hard. It equals 0. You multiply both sides by any number you want, like 1 over D3. Okay. So we have D sub 2. And somewhere we have a very friendly vector. We have that V3 is equal to this. V3 is equal to that. Okay. We know that V3 is equal to D1 V1 plus D2 V2 plus D3 U3. But we now know what D1 and D2 are. D1 is this mess. It's negative U3 dot V1 over V1 dot V1. That's D1 times vector V1 plus D2. Don't need the plus because D2 happens to be minus. Plus or minus is minus. d2 times v2 plus d3, which we said was 1, times u sub 3. So here it is. That's u sub 3. V sub 3. That is v sub 3. And you know what? It's orthogonal to v1. It's orthogonal to v2. Okay. Now, this here is a linear combination of the vectors in U, the vectors in S. In fact, it's just U1. And that's a vector in U3. So those two vectors are in U3. And V sub 2 was a linear combination of vectors in U. So the only way V3 can equal 0 is if this constant is 0, which is very possible, and this constant is 0, and this constant is 0. Oh, that's not very possible. V3 is not 0. We probably will need this in the next step. So we found V1, V2, and V3. They're all orthogonal to one another. So let's consider this set. V1, V2, V3, and good old U4. And we want V4 to be in the span of this set. That implies that there exists F1, F2, F3, F sub 4, all in the rails, such that V4 is equal to F1 V1 plus F2 V2 plus F3 V3 plus F4 U4. Okay, now here's the headache. We want V1, V4 dot V1 to be 0. We want V4 dot V sub 2 to be 0. And we want V sub 4 dot V sub 3 to equal to 0. Okay. Well, this is equal to V4 F1 V1 plus F2 V2 plus F sub 3 V3 plus F sub 4 U4. That's V4. Dotted with V1. Well, this dotted with that, that's going to be F1 times V1 dot V1 plus this dotted with that. V2 dotted with V1 is 0. We know that. Plus, so I won't write the 0, plus F3 V3 times V1. Well, V3 dotted with V1, that's 0. Okay, so I won't write that either. Then we have this. F4 U4 V1. And this equals 0. Let's hold on to this equation. Let's call it number 1, different from the one above. Well, this here equals V4 F1 V1 plus F2 V2 plus F sub 3 V sub 3 plus F4 U4. And I want to dot this with V2. Well, V1 dotted with V2 will be 0, even if we multiply it by the scalar. And then this dotted with that, well, that's going to equal to F2 V sub 2 dot V sub 2. This dotted with F3, F2, V2 will be 0, because V3 dotted with V sub 2 we know is 0, plus this dotted with V2. F sub 4, U sub 4. This equals 0. Let us call this new equation 2. Here, V4, F1, V1, etc. F1, V1 plus F2, V sub 2 plus F sub 3, V sub 3 plus F sub 4, U sub 4. Dotted with V3. Okay? V1 dotted with V3 is gone. V to 0, V2 dot V3 is 0. Even times the scalar. This times V3, I don't know what that equals. Plus this, F4, U4 dotted with V sub 3. We want this to equal 0. Okay, that is equation number 3. I guess this should be equal. Okay, now we need to find the coefficients so that this won't equal 0. Sorry, so I need to find F1, F2, F3, and F sub 4. So then I know exactly what V4 equals. Okay. So let's see what we can do. From equation 1, I know that V1 dot V1 is not 0. So I can solve for F1. Just bring this to the other side. So F1 is equal to negative F4 times U4 dot V1 all over V1 dot V1. Okay, so I have F1. 2. Equation number 2. I know that V2 dot V2 is not 0. So I can solve for F sub 2. F sub 2 is, bring this to the other side, is F4 U4 dotted with V2 times V2, which I knew is not 0. So that is F2. F3, bring this to the other side. And okay, bring it to the other side. Bring all of this to the other side, and you'll get that F sub 3 is F4 times U4 dot V3 all over V3 dot V3. Remember a couple of minutes ago, or maybe an hour and a half ago, somewhere I showed that V3 was not 0, like right here. V3 is not 0. So then V3 dot V3 will not be 0. Okay. So I have this. How about we say let F4 equal to 1. Okay. So we know that V sub 4 is equal to F1 V1 plus F2 V2 plus F3 V3 plus F sub 4 V4, U4. Okay. F1 is this, but remember F4 is 1. So we get negative U4 dot V1 over V1 dot V1, that's F1, times V sub 1 plus F2, which is this, where F4 is 1. So it's, that should be minus. So should that be, sorry. Minus F2, which is U4 over V sub 2 times v sub 2 plus f3, that's 1. So that's minus u4 dot v3 over v3 dot v3 plus f4, which is 1, times u4. Okay, now I do have a question about, or a concern about f sub 3, and I'm not sure what happened, but the numerator is taken into account, that's a 1. The numerator is u sub 4 dot v3, and somehow I didn't put the dot v3. Now I did. Okay, so this here is v sub 4. And let's see what mistakes I made. This minor. This is f1 times v1. That's exactly right. Then I should have f2 times v2. Here's my f2. There's my v2. Plus f sub 3, which is right here, times v sub 3. Sorry about that. So there is v4. So now I have that v1, v2, v3, v4 are orthogonal. And basically, what I want to do is, I want to add on u5, and then let v5 be in the span, and then make sure that v5 is orthogonal to v1, 2, 3, and 4, and then cross this out and put v5. And keep doing this process. And that's where the rest of the proof is heading towards. So, as I said, we're just going to continue. We continue this process until we get a set of m orthogonal vectors. And this set, by construction, is v1, v2. I mean, we're calling them v vectors, will equal to this. But this is T star. That is what we call T star, which will be the orthogonal orthogonal vector space of W. Okay, so what I want to say is, it follows that T star is an orthogonal basis for W. And now we're almost done. So we have this basis, orthogonal basis for W. Now, how do you make an orthogonal basis or orthonormal basis? Basically, how do you make any orthogonal set an orthonormal set of vectors? Okay, so what you want to do is let W sub I equal to V1 divided by the length VI divided by the length of VI. This will be a unit vector. And what do I want to say? And I want to say for all I equal 1 to n. I claim that T equals W1 up to Wm is an orthonormal basis for W. Now, just scaling the vectors is not going to change that it's a basis. If you have a basis, where are we? You have the basis here. If you scale every vector, in other words, was it T star? T star is equal to V1, V2, up to V sub n. Up to V sub n. Well, if you make a set T double star by dividing each vector by some non-zero number, this is still going to be a basis. This is still going to be a basis. I mean, why is that? Well, to show, okay, well, suppose C1 times V1 over C plus C2 times V2 over C all the way down to C sub n, V sub n over C is equal to 0. But this is the same as C1 over C times V1 plus C2 times V2, C2 over C times V2 times vector V sub 2 all the way down to this scalar times vector V sub n is 0. But since these vectors are in a basis, and I found a linear combination that gives me 0, that implies that C1 over C equals C2 over C, which equals 2, or C sub n over C equals 0. But that means that the numerators had to be 0. The numerators have to be 0. But that's what I wanted. I wanted to show that if I found the linear combination of vectors in this set that equals 0, that C1, C2, up to C sub n all had to be 0. So I have that down. Now, so this is still our basis. Okay, so linear is m linearly independent vectors in the set W, which has dimension m. Okay, remember, S was the basis for W with m are vectors. Then any set with m independent vectors in W must also be a basis. So T has to be a basis. Okay, now we just want to show one last thing. Are those vectors in our T orthogonal? Is W sub I dotted with W sub j, where I and j are different? Does this equal 0? Well, I know one thing. This equals Vi over the length of V sub I dotted with V sub j over the length of V sub j. And this is the same as this times dotted that. That is, it's 1 over V sub I times Vi dotted with 1 over the length of V sub j dotted with V sub j times V sub j, no dot. Okay. Meant to put the bracket around here. Okay. So now what I have is is a scalar times v sub I times another scalar, say C1, and C2 times v sub j. Well, I know that this here, we proved it earlier. This is C1, C2, not earlier today, but in another video, equals that. That is, this equals to 1 over the length of VI times 1 over the length of V sub j times VI dot V sub j. That's 0. And this fraction is a non-zero number, and this fraction is a non-zero real number. And when I multiply those non-zero numbers with the number 0, I get 0. Okay, I get 0. So I proved it. That set T, I proved my claim. This set T is orthonormal. Hence, T equals W1, W2, all the way up to W sub M is an orthonormal set. Sorry, forget set. It's an orthonormal basis for W. And we constructed it. Now that's real mathematics. The constructive proof is always exciting because sometimes you can prove the existence of something without even finding it. You can prove that there's a number that has these 10 properties. But you know what? You can't write down the number. But you proved it exists. Go and find it. Here, we don't have to go and find it. We constructed it. If you like long proofs like this, please don't come back again. But if you do like videos like this, please subscribe to my channel. I meant you shouldn't come back because I don't want to do any more long proofs like this. But kidding aside, subscribe to my channel. Tell your friends and family members about my YouTube channel. See you guys in the next video. Please watch and learn.